We've already seen this amazing animation, simply pushing a box across the floor. Now we all know that the box slows down because of friction, but how much do you know about friction? When we look at sandpaper, it's easy to understand why there's so much friction with a substance like this. Just imagining it, you can almost feel that rough surface grating against your skin. If we look even closer, it's even more obvious. You can see the roughness, all the bumps on the surface. So when you go back to motion like this, I get that this is just a simple cartoon picture, but I'm sure you can easily imagine a smooth box sliding across a smooth floor. The thing about smooth surfaces is that if you zoom in far enough on them, at a microscopic or even atomic scale, they're actually still rough. And when you look at it this way, it's easy to imagine all those jaggedy edges catching on each other and really grating against each other. What's actually happening at an atomic level is there's temporary bonds that are forming between the two surfaces. And then as the motion proceeds, it's forming those bonds and then ripping them apart. So that's why motional energy is being lost and thermal energy or heat is being gained. So this is really the basics of friction. So let's go ahead and just define friction in general. Friction is a force that opposes motion. The direction of friction is parallel to the contact surface and opposite the motion, or, as we'll discuss in a minute, would-be motion. There's multiple types of friction. The first example is what we call static friction, and that's when you have no relative motion between surfaces. Or in other words, the surfaces are at rest relative to each other. The second type we're going to look at is called sliding friction. That's kind of obvious by the name. It's when two surfaces are sliding across each other. It's also commonly referred to as kinetic friction. The last one we could talk about is rolling friction. That's kind of obvious. It's when surfaces are rolling across each other. We're not really going to go into that one as much right now. I'm going to focus on the two, static and sliding. Let's start with sliding friction. Here's an example. Now, I know that was pretty intense and it happened really quick. I thought about showing you a slow motion video of that one, but I figured that was just too much excitement for one video, so it's pretty obvious. I don't think there's much more we need to describe about sliding friction as far as what it looks like. Okay, here's a capture of the video. So let's just go through our general properties of friction. The motion, or what we could call velocity, is to the right. We know that friction opposes motion in general, so it's going to be to the left. And I want to point out that it's also parallel to the contact surface, which is the table in this example. I want to point out a few interesting properties of sliding friction. The first is that it increases with downward force. So what I mean is there's already downward force due to gravity, or due to the weight of the object itself. And so that weight, if the box was moving to the right here, would result in friction to the left. But if I were to push down on the box with extra force, then I would get extra friction. One way to simulate extra force is to just simply add more mass. So the more mass you pile onto an object, the more sliding friction you're going to get. The second thing is, and this is a little surprising, it actually doesn't change significantly with speed. So whether the box is sliding at 1 mile per hour or 30 miles per hour, there's really not much of a difference between the friction that you'd measure. So we just simply say that there's no change with speed. The last thing, and this often surprises people, is that the friction doesn't change with surface area. So what I mean, if I look at my box up here, if I were to spread that box out, So there's more surface area. Turns out that it doesn't actually change the friction. And again, that often surprises people because it seems like it should. But the issue here is its weight distribution. So if you're spreading it out, you're simply distributing the weight more, and there's less downward force per area. So you just get less friction like in that little area. So overall, there's no change. So when you see those extra wide tires on trucks, they don't do it because of friction. These wide tires aren't going to help this truck stop any better. Now, traction's a little bit different, and that's another issue that I won't get into here. But as far as friction goes, it doesn't help in that situation. Let's look at a big heavy dump truck. So this picture that I'm showing you here, imagine there's 4 wheels, 2 on each side. So what if we were to add 8 more tires? Would that give the truck more friction? And the answer is actually no. It would help spread the weight, so it's good for weight distribution, and it can result in less wear and tear and less heat generated by the tires and the parts of the truck, but it doesn't actually give it more friction. And when you really care about that is, like, for example, a stop. If you were to come to a skidding stop, more friction would be helpful, but in this case, you actually don't get any more by adding more tires, so it wouldn't actually make it stop any quicker. Here we're looking at static friction. The table is tilted in this case. When you're dealing with static friction, I found it's helpful to always start with a question: would there be motion if static friction disappeared? I'm sure you can imagine that if this table surface suddenly became smooth ice, the book would just slide down. So if your answer is yes, that leads to a second question: in what direction would the motion be? Well, we just mentioned that it's going to be down, so we'll make a note of that. That's what I'm going to call the would-be motion, because technically the book isn't moving. So it would be sliding down, so the static friction would be opposite that. And notice that it's parallel again to the contact surface. Not parallel to the horizontal, it's contacting diagonally like that. Here's a demonstration of how static friction can actually turn into kinetic friction, or what we call sliding friction. Yeah, exciting, huh? So that's the basics of static friction and sliding friction. Here's another situation. Imagine that the table is perfectly level. What type of friction is being demonstrated in this image? It's actually kind of a trick question. It's not demonstrating any friction. There's no motion and there's no would-be motion. If the table really is perfectly level, and imagine the table suddenly became really, really smooth ice, the book still wouldn't go anywhere. There's no reason for it to. Let's look at this situation. Here I have my trusty box, but on top of that I've got another box. They're held together just by friction, and then I'm going to shove the bottom box. Okay, let's go ahead and imagine that they stayed together throughout that trip. In this case, what type of friction was demonstrated in this example? Let's look at a point during its motion. There's obviously sliding friction because the bottom box is sliding across the floor. That's going to be pointing to the left because it's opposing the motion, and it's also parallel to the ground. In this example, there's also static friction. And you might be thinking, well, wait, didn't you say that there had to be no motion for static friction? And the answer is no. What I said is there had to be no relative motion. So for static friction, I like to ask that question. What would the motion be if static friction suddenly disappeared? You can imagine that for this purple box, if this was suddenly really smooth ice, when he shoved the bottom box, that purple box would have fallen off in the backwards direction. So its would-be motion is to the left. That means that static friction is pointing to the right. It's actually good that it works out this way, because why else would the purple box go forward with the bottom box if it wasn't actually being pushed in that direction? So you have to be careful with static friction, because in this example it almost seems like static friction is pointing in the direction of motion. And it is in terms of the object as a whole, but it's actually pointing opposite the direction of the would-be motion, and that's the key. As another example of why static friction is good, that it works that way, is, just think of running or driving a car or anything where you're propelling yourself forward. How is it that a runner can push himself forward? It's because of static friction. Because the would-be motion, if you think about it, if you ever tried to run on ice, if this was really smooth ice, his foot would just slip backwards. So the would-be motion is backwards, which means that the static friction is actually forward, and he can use it to propel himself forward. Here's a new question. What is stronger on an object, static or sliding friction? Let's use our image for static friction. We're going to apply our understanding of forces. We know that gravity is pulling it straight down. Gravity always pulls straight down. The book is being supported, but unlike all the previous forces I've shown you with support force, this one is actually tilted because the surface is tilted. So the support force is always perpendicular to the surface. So in this case, it's not directly opposing gravity. Well, because gravity is a vector, and we haven't really gone into this much, so I don't want you to worry about it too much, but this vector can actually be decomposed into different parts. So here I'm going to use this direction of the support force as my reference direction. In that case, the gravity has a component like this, but it also has a component like that. So these two together make up the gravity vector. When you look at it this way, you can see that gravity, in this case, is basically pulling the book down the table. And you could also look at this with a perfectly vertical system, and then you would get a component of the support force, and in that case you would say it was pushing the book down the table. But either way, the book wants to slide down the table. Static friction, we know, is parallel to the surface, so it's going to be in that direction. So static friction is really what's opposing this force that's trying to push it or pull it down the table. The more we increase this angle, the stronger that push or pull is going to be, so the stronger static has to be to oppose it. So if static friction was weaker than sliding friction, what would happen in this example? If that was the case, the book should be sliding down the table, and it's not, so that suggests that static friction has to be stronger than sliding friction. Here's another way to think about it. If you've ever tried to move a large, heavy object by sliding it across the floor, you probably know that it's hard to get it going, but once it's going, it's easier to maintain that. Well, that's another consequence of sliding and static friction. The static will build up to a stronger point. Once you can finally break that static friction, though, then you move into a weaker sliding friction, and it's not as resistive to move it across the floor. We could go deeper into the specifics of static friction and sliding friction, but for the purposes of this course, I think this level is appropriate.